right, good morning. Okay, first thing first. We got this exam coming up in a day in a week. Okay, so exam 1 will be on Thursday, September 21st, 6:30 p.m. to 7:30 p.m. Get there a little bit before 6:30. The earlier you get there, the earlier you get to sit down and settle down a little bit. We'll be in Elliott Hall. That giant hall in Elliott actually has a room number. It's 116. Okay, so that's the place we'll be in. Now, when you get there, you will be seated based on who your recitation TA is. This thing is also posted on the course webpage, so take a look at that when you get a chance. Let me zoom in a little bit more. The top of this is the front, the stage of the hall. So, for example, if your recitation TA is Siddhant Suttar, you will go to the front and in this general area. Just look for your recitation TA, and he or she will guide you where you need to be. If you can't find your TA for any reason, I will be on the stage. Find me, and I'll get you to where you need to go. Okay, so once again, make sure you take a look at this on the course webpage. I'll be showing this every time we have class, starting from now until we have the exam. All right? And I have more to say about the exam in the next few days. Oh, by the way, how many of you went to the test drive? Okay, how was it? It was a big place, hectic place. Okay, well, if you went, you had a pretty good idea of what it'll be like the night of the exam. All right, so today we're going to look at section 2.8. This derivative thing we saw last time is very, very important in calculus. We'll be looking at it for quite a while. So a brief recap. We found out that the derivative, and by the way, keep in mind, we want to keep in mind the geometric significance of the derivative. This is the slope of the tangent line, which translates into the instantaneous rate of change of whatever function you're looking at. And last time we found out that the derivative of the function f of x at x is equal to a can be expressed in two ways. This was the first form that we looked at. And the second form that we looked at, remember, they're identical things, just different ways to express that same quantity. The important thing to note here is that both of these things will only give you a number, right? Once you decide what a is equal to, both of these will give you one number that corresponds to that particular a that you have chosen. So if I want to find the derivative of a function at a different a, I have to use a different a each time. Now, the idea today is to, instead of looking at it that way, getting 1 point at a time, why don't we relax the requirement of saying at a specific a and just say at any given x that we want to look at? We'll leave it as just yet to be determined value of x, and the outcome is the derivative as a function of x. So you get an entire function that if you want to plug in a different a at a later point, all you do is plug in that a into the new function you got, as opposed to doing this each time for a new value of a. So what do? The easiest way to do this is to look at the second form right here. All you got to do is change this a to x. Very, very simple. Now we say that the derivative of the function f at any value of x is simply exactly what the function here says. But instead of talking about a specific number for x, we leave it as x. The first form is not a very convenient form for that purpose. If I change this a to an x, it doesn't get me anywhere. I get 0 over 0, at the limit of 0 over 0. That doesn't get us anywhere. But the second one, just one slight tweak, and now we got a function. So this function has a graph, has a domain, has a set of range, and all that stuff that every function has. Now what do you do with this? You use this exactly the same way you used the second form of the derivative at a. All right, so quick example. Let's say that the function is radical x. By the way, let's make a note of the domain here. What's the domain of this? 0 to infinity including 0? Yeah, you can take the radical of 0, right? So 0 to infinity is the domain. And now let's use that thing in the box on the last page to find the derivative of this at any x of our choice. Well, almost any x of our choice. I'll first write down that formula again. This is f of x. F of x plus h means you replace every x you see in a function with x plus h. Okay, so the function f of x turns into radical x turns into radical x plus h. F of x is whatever it is over h. And as usual, you can see when h goes to 0, we approach 0 over 0. That means there's more to do. We've got to figure out what's causing that, get rid of it, and then go from there. Okay, we've seen these root things so many times. What do you do when you see a root expression? Rationalize, exactly. Let's rationalize the numerator here. It's a pretty neat trick that's useful in a lot of future classes too. You encounter something with root that you can't find another way to deal with, rationalize it and see where it goes. Numerator is x plus h. Right? This thing squared, so it's x plus h minus radical x squared, and that's radical x. Don't do anything to the denominator. Don't multiply this out. It rarely helps. All right, so let's see. Top is h. Downstairs has an h times something else. When h goes to 0, as long as h is not exactly equal to 0, these can be canceled, and we will. And finally, when h goes to so close to 0, this is approximately radical x. Radical x plus radical x is 2 radical x in the denominator. All right, so this tells me that the derivative, the slope of the tangent line, any point on this function within the domain, almost any point within the domain, can be found by using that function. What's the domain of this? Right? What else? That's right. So the same as this one with the 0 removed. Right? So this is 0 to infinity. Yeah. I can take the radical of any number, any positive number. Right? Rationalizing, you could rationalize this again if you don't want the radical downstairs. You could do that. But it's the same thing in the end. And when we talk about domain, we don't really worry about what it looks like. We worry about what kind of number that x can be. So I think it's okay to leave that expression as is, but just worry about what x can be. Okay, so this brings a very important point that you want to keep in mind. The derivative of a function can have different domain. But that's one location. We'll investigate what's going on here in a little bit. Okay, but that's one point, one thing that I want you to keep in mind from this point on. You can find the derivative of something, but it doesn't have to have the same domain. A lot of functions that we deal with have the same domain, but it's not a requirement. It's an entirely different function with its own domain, with its own range. Okay, so let's see what happens at 0 here and why 0 is not there. We know why 0 is not there from looking at the algebraic expression. But let's look at why from a geometric point of view. First, let me sketch radical x. What does radical x look like? Parabola opening to the right. Which half? The entire thing? Upper half. Very good. How do I get the lower half? Yes, negative in front of that will get you the lower half, opening to the right. Good. Very good. The derivative we just found is 1 over 2 radical x. Now remember that derivative tells you the slope of the tangent line. So let's say if you go to 1 here, for example, the tangent line, which approximates the slope at that location, is just a perfectly fine number. It's perfectly okay. It could be 1, it could be 2, whatever. It's a perfectly fine number. Now notice what happens at 0 right here. When you go to 0, it becomes very, 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 very steep. In fact, at 0 exactly, this thing is exactly vertical. And what's the slope of a vertical line? Undefined. It doesn't exist, right? Okay, and that's the reason why this thing doesn't have 0 as a domain. If you graph this thing right here, if you just look at this as a function and try to graph it, when x is very small, the denominator is very small, so f prime is very big. It'll be very, very, very big. And when x is very large, this eventually becomes very small. So it looks something like this. Okay, the vertical tangent at x is equal to 0 is why f prime of x does not have x is equal to 0 in the domain. We're trying to tie together the algebraic thing, just looking at this as purely a function, algebraic function by itself, and the geometric picture behind it. That's one of the very important link that calculus established. Before calculus even got invented, geometry and algebra were two completely different things. But calculus tied the two together. Now we have a very, very clear connection between the two. That's why sometimes you see the words analytic geometry with calculus when you look at textbooks, for example. That's essentially what this is all about. Okay, so if f prime does not exist, at some x, we say the function is not differentiable. At that particular value of x. So here we would say that the function radical x is not differentiable at 0 because f prime fails to exist at 0. The word differentiation means to find the derivative. Not differentiable means you cannot differentiate that function because it does not have a derivative. Okay? And once again, every point on this function right here represents the slope of tangent line at the same point. So this value right here is the slope of the tangent line on f of x at same value of x. This point right here represents the slope of the tangent line at that point. This point represents slope of tangent line at this point, and so on. Okay. Now this actually provides us a way to sketch the graph of f prime if we have the graph of f. If I have a graph like this, I can simply try to spot the tangent line slope and use that information to sketch a graph of f prime without actually finding the functions themselves. And let me show you how that works. I'm going to sketch the graph of some function. Something like that. And we're going to use this, just this right here, to sketch what f prime might look like. I don't even know what f looks like, so I cannot use the formula we had on the last 2 pages ago to find my derivative and sketch it. I have to rely entirely on the graph of f to come up with a graph of f prime. Okay, so let me draw a new set of axes right below it. And I want all the x values to line up. Okay, so keep in mind that every single point on the graph of f prime represents the slope of the tangent line on the graph of f. Let's start with 0 right here. At 0, my tangent line looks kind of like this. Right? It's a horizontal line at the point where this thing is turning. All the tangent lines here are negative. All the tangent lines here are positive. So halfway between the two, the transition right here, we have exactly equal to 0. So this thing has 0 slope, which means f prime of 0, the slope of the tangent line at x is equal to 0, is equal to 0. And that represents 1 point on the graph here. F prime of 0 is 0, means we get 1 point right here. Okay, does that make sense how I got that point? Yes? Good. Now let's go over here. Let's draw a couple different tangent lines. Way near the right here, we have some positive slope, right? And halfway between the two, we have this right here, some other positive slope. Right. You notice that as we move to the right, the tangent line slope remains positive, and it gets steeper. Okay? It's 0 right here, gets a little steeper, a little more steeper, much steeper. The more we move to the right, the steeper the tangent line is. And that means bigger and bigger positive f prime of x. So this here might be 1, this here could be 2. If I keep going here, at some point I'll probably find a slope where it's equal to 10, for example. Now how would I represent that kind of behavior on this graph here? Say it again. It will increase, maybe not linearly, depending on exactly how this function is, but you're right, it will increase. For example, like I said here, let's say this thing has a slope of 1. So at that same x, let's say this is 1. Right? Let's say this thing has a slope of 5 or whatever. So at that same x right here, I would have a slope of 5, whatever. Let's say right here. As I move to the right, I expect higher and higher positive f prime. So I should have something that resembles this kind of behavior. Linearly or not, depending on exactly how the tangent line slopes are behaving and what the function is doing. But one thing we can be absolutely certain is that the more I move to the right, the higher the value of f prime should be. Does that make sense? Everyone? Good. How about on the other side? What do we see? As I move to the left, what do I see in terms of tangent line slope? More negative, absolutely. So we start at 0 right here. I move over here, I have a negative slope. That could be -1, for example. If I move over here, I get a tangent line slope that could be -12, for example. It's a much bigger negative number than this one. The more I move to the left, the bigger negative number I see. So as we move left, tangent line slope becomes more negative. More negative is fine. To clarify, larger negative f prime of x as we move to the left. Okay, so I might expect something that looks kind of like that. Do you agree? Is that a reasonable representation? Yeah? The more I move to the left, the larger and larger the y value. The y value on this graph right here represents the tangent line slope at the same value of x. And notice that we sketch f prime without even knowing what f is. We can probably guess what this f is, but that is irrelevant. Let's try another one. And as usual, this right here is the graph of f. Let's have it look like this. Something like that. And we'll do exactly the same thing as we did. we'll look at the graph, the features of this function right here, and come up with a reasonable estimate representation of what f prime might look like. Again, all the x values will line up, so roughly line up here. The best way to start something like this is to find out where the tangent lines are horizontal to start, because you know those represent the x-intercept on the f prime graph. Let me write that down. Horizontal tangent line, a horizontal line has zero slope. So if I could find out where those things happen, then I know I have x-intercepts on my f prime graph. At those x's, f prime will be precisely 0. And I see 3 locations of that. And this one just kind of flattens out. So here's one. At this location here, tangent line is flat, right? It was positive before, negative after. So perfectly flat. Roughly here, same thing happens. Positive before, negative after. At some point, there's a transition, and it happens right here. Similarly, here we have another flat tangent line. And regardless of what is going on anywhere else, I know I have 3 points I can absolutely be sure about on the graph of f prime. Because right here, at this value of x, f prime is 0. At this value of x, f prime is 0. At this value of x, f prime is 0. And those 3 points I know for sure have to exist on there. Okay. Now the next thing you do is to kind of check out what's in between these. Once you find these, you just got to check out what's going on between any 2 and to the right and to the left of all the remaining ones. Let's start between these 2. Looking at the graph right here, this is a 0 slope. And then we have a negative slope. It kind of increases, becomes more negative, and eventually settles back down to 0. So this entire region right here has negative tangent line slope, which means that the graph representing f prime has to be entirely below the x-axis on the f prime graph. Does that make sense? Okay, let me write that down too. So this means this portion is below x-axis on the f prime graph. Right? F prime is negative tangent line, and that entire portion must live below. It has to start at 0 and end at 0. It has to be negative the entire time. And so what do you think the shape over here might look like? Something like a parabola sounds pretty reasonable. Has to be 0 here, and always negative no matter what. So we can have a pretty reasonable guess, something like that. Right? It has to start at 0, has to be negative, all this entire region right here, and has to come back to 0. The shape may not be exactly right, but the feature, as far as it being below the x-axis, 0 on here and here, that we can be absolutely certain. All right, does that portion, what I sketch here, make sense to everyone? Okay, how about this portion right here, between here and here? What do you think? Yeah, that's a reasonable observation here. This portion right here is entirely positive. Tangent line is always positive. Start at 0, end at 0. Must be always above the x-axis on the f prime graph. So that portion right here would give me something that looks like this. Always positive, start at 0, end at 0. So that and that are sketched using the same reason. Again, exact shape, how wide and how low they get, we don't know that for sure. And actually, that's not really the point of an exercise like this. The point is focus on the general feature, the shape. Okay, now to the right over here, to the right of this right here, on this portion, what do you notice the tangent line is doing? And let me hear from somebody else over this side this time. What do you notice the tangent lines are doing on this portion of the graph on F? Negative, and is it getting more negative as we move to the right, or getting less negative? It seems to be flattening out. Does it get to exactly 0? We don't know. But we can say for sure, you're absolutely right, that this portion has negative slopes. And it is slowly, slowly getting back to 0 because we're seeing this flattening out region right here. So negative f prime. And we also see it slowly becoming, let's say, closer to 0. Because this region is suggesting that this might be a horizontal asymptote, and things are slowly flattening out. So good. All right, same reason here. Negative f prime, it must be below the x-axis on the f prime graph. Gets closer and closer to 0 as we move to the right. So we might get something that has to be below, right? Has to be below. And as we move to the right, closer and closer and closer and closer to 0. The flattening out region, the flattening out feature here tells us that the f prime is getting closer to 0. I'll write that down here too. F prime gets closer to 0 because f of x is flattening as x increases. Okay, now we got all the features except this end right here, this tail end right here. Now if this part makes sense to you, then this part is not very difficult. It's just the opposite of that. All the slopes are positive, and it seems to be starting near 0, remaining positive. So I should get something that looks, so it's starting close to 0, has to get to positive, become more and more positive, and eventually comes back to 0. Something like that. And once again, how high and how low these things get, we don't know. So how high we can determine from shape alone. But we know all these twists and turns and all the x-intercepts are going to be right. Okay, does this make sense to everyone? Any question on this example? Yeah. Here? Right here. What about it? Yeah, I didn't mean to draw it that way. I wanted to mirror this side. So let's just say it kind of flattens out and then increases. So I don't really see a negative slope here. I see zero slope, nearly zero slope, positive, positive, gets bigger and positive, more positive, and flattens out to zero. We're looking at a slope. Does that make sense? Okay. Other questions? Okay, now you can actually use exactly the same reasoning we've established here to start with a graph of f prime and kind of guess what f might look like by using exactly the same reasoning in reverse. We won't do that right now, but if you can sketch f prime from f, in principle, you can sketch f from f prime. Now let's get back to the point I raised earlier. Remember that f and f prime can have different domains. And this means that even if f is defined at some x, f prime may not be. It's possible. And so that means if it's undefined, then we can have one of two things happening. Either there's no tangent line at all, or a vertical tangent line. So let me list some requirements for f to have a tangent line. Rather I'll list things that can break f. So f is not differentiable if the first one is the one we saw earlier. Differentiable, let's say, at x is equal to a. First one, we saw this earlier, vertical tangent line at x is equal to a. And you can refer back to the first example we did to see that situation. The second thing that can happen for the tangent line to fail to exist is if f of x has a discontinuity at x is equal to a. It could be an open circle, it could be a jump discontinuity, it could be an asymptote. So here's an example of that. We have an vertical asymptote at x is equal to 1, a clear discontinuity. So this means that f prime of 1 does not exist. Now, how would you try to place a tangent line at the asymptote right here? You can't be there. You cannot be on the function there. So therefore, there's no way for you to place a tangent line there. And this applies to all kinds of discontinuity. The third condition is when f of x is not smooth at x is equal to a. So this is when you see, for example, a cusp or a corner. Right here, this is the absolute value of x graph right here. The corner at here means that f prime does not exist. And again, think about geometrically, how would you place the tangent line there? The tangent line has to kind of approximate what the local slope on that function is. At this sharp corner here, how would you do that? Would you balance that? Would you use the right branch or the left? It's not clear how you would do that. And think about this, the process of drawing a secant line and using that to get a tangent line. If I draw a secant line here, from here to here, and bring the second point closer and closer to here, if I look at just the right side, it always looks positive. If I use the secant line using a point on the left, it always looks negative. So how can I reconcile between negative all the time, half the time, and positive half the time? It's not clear how that can be done. And here's a similar situation, a cusp. And by the way, the equation for this graph right here is y is equal to x to the 2/3. I'll write down the equations for these guys. This cusp right here also has the same feature. F prime does not exist. Once again, think about how you would use secant line to approximate the tangent line. If you use a point to the right, the secant line is always positive. If you use a point to the left, the secant line is always negative. At the point right there, how would you reconcile the two? Okay, one last thing before we end here. This is kind of important. If you know something is differentiable, if you know f prime exists, then you know f must be continuous there. So what, in a more concise way to say that, is differentiability implies continuity. If I know f prime exists at some location, that guarantees that f is continuous there. Because we know that if f is not continuous, then we don't have an f prime. The reverse can be used to say that. But not the other way around. Just because a function is continuous, it does not mean it is differentiable. Okay, we'll have more to say about that in a future lesson. That's it for today. See you Friday.